Hello everyone, welcome to Wings of Physics. Myself Deepali Kulkarni from PVP Junior College, Pravaranagar, Loni. Today we will study the chapter Thermal Properties of Matter in one shot. Okay, let us start. What is the meaning of matter? Matter कशाला म्हणायचं? Matter, it is a substance which occupy a space and which is having mass, means it is having inertia, that is called as matter. Solid, liquid and gases, these are three states of matter. And thermal properties means we supply heat, at that therm means heat, and we supply heat to solid, liquid and gases. At that time we have to study its properties, and that is the meaning of the thermal properties of matter. Now we have to study what is the concept of heat and temperature. Therefore, we have to distinguish in between heat and temperature. Question may ask, distinguish between heat and temperature. Okay. Then first point, that is nothing but the definition of heat. What is definition of heat? Suppose consider two bodies. First body, that is water. It is having temperature 30 degrees Celsius and a heavy metal sphere, that is called as a bob, and it is heated at high temperature, that is 80 degrees Celsius. And these two bodies, they brought in contact with each other. Then what happened? When these two bodies, they brought in contact with each other, then we know that heat always flows from higher temperature to lower temperature, and therefore heat is transferred from this hot body to this cold body, and up till the temperature of this system that becomes same. Means when two bodies, they are at two different temperature, they contact with each other, then there is a transist of energy. It is a form of energy. Transist means transfer, and therefore the definition of heat is that heat is energy transist when two bodies are at different temperature, brought in contact with each other, then they exchange the heat, and that is the definition of heat. Then what is temperature? Temperature, that is the measure of degree of hotness or coldness. एखाद्या बॉडीचा गरमपणा किंवा थंडपणा मोजायचा असेल तर आपण जी फिजिकल क्वांटिटी वापरतो तिला आपण टेम्परेचर असं म्हणतो. आणि म्हणून डेफिनेशन काय बघा, आणि एखादी थर्मोडायनॅमिक सिस्टीम असेल, समजा ही थर्मोडायनॅमिक सिस्टीम आहे आणि ती कशाने व्यक्त होते, तर ती त्याचे थर्मोडायनॅमिक्सचे स्टेट व्हेरिएबल्स असतात, प्रेशर, व्हॉल्यूम आणि टेम्परेचर. पैकी टेम्परेचर ह्या व्हेरिएबलद्वारे आपण थर्मोडायनॅमिक सिस्टीमची स्टेट डिफाईन करू शकतो. आणि म्हणून व्हॉट इज द डेफिनेशन ऑफ टेम्परेचर? Temperature is a physical quantity, and with the help of that physical quantity we can define the thermodynamic state of a system, and that is the definition of temperature. I repeat, temperature is a physical quantity. With the help of that physical quantity we can define the thermodynamic state of a system. Then second point, we can measure heat with the help of calorimeter. We can measure heat with the help of calorimeter, and we can measure temperature with the help of thermometer. Second point, we can measure heat with the help of thermometer. Then third point, heat is derived quantity, because heat, that is nothing form of energy, and energy is derived quantity, and therefore heat is derived quantity. Heat is derived quantity. Derived quantity. And in first chapter, units and measurement, we studied that temperature is a fundamental quantity. It is fundamental quantity. fundamental quantity. Then, next point. SI unit of heat, that is joule. SI unit, joule. And SI unit of temperature, that is Kelvin. SI unit, Kelvin. Then, last point. Dimensions of heat, that is nothing but dimensions of energy or dimensions of work, and that is L raised to 2, M raised to 1, T raised to minus 2. That is the dimension of heat. And dimension of temperature, L raised to 0, M raised to 0, T raised to 0, capital K. This notation is used to determine the temperature, capital K, and K raised to 1, and therefore dimensions of temperature, that is L raised to 0, M raised to 0, T raised to 0, K raised to 1, and this is the difference in between heat and temperature. Okay. Then according to the caloric theory, when a calorie is supplied to the system, at that time its heat that gets increased, and if we remove the calorie from the system, at that time heat of that system that lost. Understood? According to the caloric theory, when we add calorie to the system, its heat that gets increased, and when we remove the calorie from the system, its heat that gets decreased. And according to the dynamic theory, the temperature is measured, that is nothing but the average kinetic energy of a system. According to dynamic theory, the measure of temperature, that is nothing but average kinetic energy of a system. Average kinetic energy of system means temperature, that is nothing but the average kinetic energy of the system. Okay. Now we have to study what is the interatomic spacing between solids, liquids and gases. Next point, interatomic spacing in between solids, liquids and gases. In case of a solid, interatomic spacing is 1 Armstrong unit. That is nothing but 10 raised to minus 10 meter. In case of liquids, interatomic spacing, that is 2 times than the solids, that is nothing but 2 Armstrong unit or 2 into 10 raised to minus 10 meter. And in case of a gases, that is 10 Armstrong unit, and that is nothing but 10 raised to minus 9 nanometer or 10 into 10 raised to minus 10 meter. And this is the interatomic spacing in case of solid, in case of liquid and in case of gases. Understood? Then we have to study measurement of a temperature. Measurement of temperature. Measurement of temperature. Measurement of temperature. Before studying this point, we have to study the difference between adiabatic wall and diathermic wall. Adiabatic wall and diathermic wall. Diathermic wall. First point, consider a two systems. system A and system B. And in between these two systems, a thick wall is present. And due to that thick wall, the system A cannot exchange heat with system B, or system B that cannot exchange heat with system A. And this ideal wall that is present in between two systems, that wall is called as adiabatic wall. Means a ideal wall or a thick wall due to which the two systems, they cannot exchange heat with each other. That wall is called as adiabatic wall. And diathermic wall, again consider two systems A and B, and a thin partition or thin wall, it is present in between these two systems so that they can exchange heat energy with each other. Means heat can flow from system A to B and system B to A, and that wall is called as diathermic wall. A wall which is present in between two systems and due to which heat can exchange. A thin wall present in between two systems and due to which that two systems can exchange heat with each other, that wall is called as diathermic wall. Then it is perfectly insulator. Perfectly insulator. Perfectly insulator. And this is perfectly conductor. Perfectly thermal conductor. Perfectly thermal conductor. Or we can say that this wall is not perfectly insulator or perfectly thermal conductor. You can write any one sentence. Okay. Then third one, wood, plastic, glass, that are the examples of the adiabatic wall, and it is not a practically present, and a thin partition of copper that acts as a diathermic wall. Okay. In calorimeter is made up of copper material, and therefore copper acts as diathermic wall. And last point, it is represented with the help of a thick portion with slanting lines. This is the slanting lines, and this is a thin partition. Okay, and this is the difference between adiabatic wall and diathermic wall. I hope all of you understood this difference very well. Then next point, that is the concept of thermal equilibrium. Concept of thermal equilibrium. Concept of thermal equilibrium. Thermal equilibrium. Thermal equilibrium. If two systems, system A and system B, they are at same temperature, at that time we can say that they are in thermal equilibrium with each other. Suppose system B is having temperature 40 degrees Celsius and system A is also having temperature 40 degrees Celsius. Then we can say that these two systems, they are in thermal equilibrium with each other. And by using the concept of thermal equilibrium, we have to state the 0th law of thermodynamics. What is 0th law of thermodynamics? 0th law of thermodynamics. 0th law of thermodynamics. 0th law of thermodynamics. Now, figure A, three systems are there. System A, system B and system C. Again, in figure B, consider three systems, system A, system B and system C. And this double arrow indicates that the system is in thermal equilibrium with each other. Now figure C, system A, system B and system C. Now in figure A, system A and B, they are in thermal equilibrium with each other. And in figure B, the system A and system C, that is in thermal equilibrium with each other. Means this system is having 40 degrees Celsius temperature and this system is having 40 degrees Celsius. In this manner, this system is having 40 degrees Celsius temperature and this system is also having 40 degrees Celsius temperature. Then according to these two, the system B and C, that is in thermal equilibrium with each other, means it is having temperature 40 degrees Celsius, and that is nothing but the 0th law of thermodynamics. Means system A and B is in thermal equilibrium with each other and system A and C is in thermal equilibrium with each other. Then system B and C, that is in thermal equilibrium with each other, and we have to study this law in 12th standard in the chapter thermodynamics, and that is the 0th law of thermodynamics. Okay. Now we have to study the two definitions, that are ice point and melting point. And before studying this definition, we have to study the definition of the thermometry. What is the thermometry? We just now studied that the temperature is measured with the help of thermometer, and therefore thermometry, that is a branch of science. In that branch, we have to study the temperature or thermometer and its measurement, and that is called as thermometry. म्हणजे टेम्परेचर जिथं ज्या सायन्समध्ये मोजलं जातं त्याला म्हणायचं थर्मोमेट्री, आणि हीट ज्या सायन्समध्ये मोजली जाते त्याला म्हणायचं कॅलरीमेट्री. ओके. नाउ वी हॅव टू स्टडी द टू डेफिनेशन्स, दॅट इज आईस पॉइंट. आईस पॉइंट, आईस पॉइंट or freezing point of water. Freezing point of water. Freezing point of water or melting point of ice. Melting point of ice. Okay. Now suppose this is a water, and if we freeze that water, then the point at which the pure water freezes, okay, this pure water freezes at particular point, and at that time pressure is 1 atmospheric pressure, and therefore that point is called as a ice point. Understood? Ice point is that point at which pure water freezes at 1 atmospheric pressure. At 1 atmospheric pressure, and that point is called as the ice point. It is also called as freezing point of water, or it is also called as melting point of ice. Okay, and that is lowest temperature. Then we have to study the steam point. Definition of steam point or boiling point, or boiling point. Boiling point. Now this is a pure water and we supply heat to that water. At that time it boils. It boils and the vaporizes into the steam. Okay, boils and vaporizes into steam. Vaporizes into steam, and again at 1 atmospheric pressure. At that time pressure should be 1 atmospheric pressure, and that point is called as steam point or boiling point. Understood? Then we have to define steam point or boiling point. A point at which pure water boils and vaporizes into the steam at 1 atmospheric pressure, and that point is called as steam point or boiling point. I repeat, what is the definition of ice point? A point at which pure water freezes at 1 atmospheric pressure. That point is called as ice point, or it is also called as freezing point of water, or it is also called as melting point of ice. And definition of steam point. Steam point is a point at which pure water boils and vaporizes into the steam at 1 atmospheric pressure or standard atmospheric pressure. Understood? You can use any word. And this is the definition of ice point and steam point. Now we have to study the different scales to measure the temperature. Different scales to measure the temperature. First is Celsius scale. Celsius scale. Second one, Fahrenheit scale. Fahrenheit scale. Fahrenheit scale. And third one, Kelvin scale or absolute scale. Kelvin scale or absolute scale. Okay. Now, this is a scale, Celsius scale, whose ice point at 0 degree Celsius and steam point that is at 100 degree Celsius. An interval in between two that is divided into 100 equal interval or 100 equal division, and one division that is nothing but 1 degree Celsius. Understood? And that scale is called as Celsius scale. I repeat, a scale whose ice point is at 0 degree Celsius and whose steam point is at 100 degree Celsius, and that 2 points, they are divided into 100 equal intervals or 100 equal division, and one division that is called as 1 degree Celsius. Then Fahrenheit scale. Fahrenheit scale, whose ice point is at 32 degree Fahrenheit and whose steam point is at 212 degree Fahrenheit, and that scale, that these 2 points, they are divided into 180 equal division or 180 equal interval. That scale is called as Fahrenheit scale, and one division or one interval that is nothing but 1 Fahrenheit. Then Kelvin scale, it is also called as absolute scale, and the scale whose ice point is at 273.15 degree Kelvin and the steam point is at 373.15 degree Kelvin, and these 2 points, they are divided into 100 equal division or 100 equal interval. That scale is called as Kelvin scale or absolute scale. And we can convert Celsius into Fahrenheit or Fahrenheit into Kelvin. Means we can exchange, or we know the temperature in Celsius, we can calculate the temperature in Fahrenheit, or we can calculate the temperature in Kelvin. Means interconversion of the scale, it is possible, and for that purpose we have to use a formula. What is the formula? Then the temperature Tc, that is the temperature, divided by the interval, 100 interval, that is nothing but Tf, that is the Fahrenheit scale, minus this 32 divided by, means the lowest temperature, and divided by 180 interval, that is equal to Tk, that is temperature in Kelvin, minus the lowest point is 273.15 divided by interval 100. Understood? Means Tc minus this one divided by interval, Tf minus this one means lowest temperature divided by interval, then Tk temperature in Kelvin, that is minus this one divided by interval, and with the help of this formula we can calculate the temperature in any scale. Now one question that already asked in NEET exam, and that question is, calculate a temperature at which the Celsius scale and Fahrenheit scale that becomes equal. That is the NEET exam question. Okay. Now we will calculate that scale. Now consider that scale is x, means x by 100. We will consider that temperature is x degree, and x divided by 100, that is equal to x minus 32 divided by 180. That is nothing but the 180x, that is equal to 100x minus 3200. Okay. Then therefore if we transfer this one, 80x, that is equal to minus 3200, and therefore x, that is equal to minus 3200 divided by 80. This 0 that gets cancelled, and then minus 8 4s are 32 and 0 is there, means x, that is equal to minus 40. At this value the degree Celsius and Fahrenheit scale, that is exactly equal. Understood? And that is the NEET question that is already asked in NEET exam. Okay. Then in this manner we can convert the one scale into another scale. Understood? Then we have to study the next question that may ask, define thermometer and what are the characteristics of a thermometer. What is the definition of thermometer? An instrument. It is designed to measure the temperature, that is called as thermometer. And what are the characteristics of thermometer? First characteristics, thermometer must be sensitive. Means when we insert that thermometer in any liquid, any gas, it shows quickly the temperature of that liquid or temperature of that gas. Then second thing, it has to be accurate, means the accurate measurement is done with the help of that thermometer. Third one, it should be easily reproducible. And fourth one, system attains, it is important that the system attains thermal equilibrium with thermometer quickly. What is the meaning of this sentence? When we insert thermometer, at that time the temperature of that liquid, suppose the temperature is 40 degree and it should be quickly shown by thermometer that it should be 40 degree. Means at that time we can say that system attains thermal equilibrium with the help of thermometer quickly. That is the meaning of this sentence, and in this manner we can write the answer of a question that are the characteristics of a thermometer. Okay. Now next question, obtain the ideal gas equation. Now we have to obtain ideal gas equation. Ideal gas equation. Ideal gas equation. ideal gas equation. To obtain ideal gas equation, we have to study the Charles law. Charles law. What is Charles law? Consider a fixed mass of a gas. This is a fixed mass of a gas and pressure of this gas that remains constant or that is kept constant. The fixed mass of a gas whose pressure is kept constant, then it is observed that volume of given mass of a fixed gas that is directly proportional to its temperature, absolute temperature. Understood? And when there is a direct proportion in between these two variables, at that time division of these two variables that is always remains constant, means V1 by T1, V2 by T2, that is equal to constant. And this is the Charles law. I repeat, at constant pressure the volume of a fixed mass of a gas is directly proportional to its absolute temperature, that is Charles law. Then second one, Gay-Lussac's law. Gay-Lussac's law. Again, for a fixed mass of a gas, when its volume kept constant, then pressure of given mass of a gas is directly proportional to its absolute temperature. Again, the direct proportion is there, therefore we can write P1 T1 that is equal to P2 T2 that is equal to constant. This is the Gay-Lussac's law. Then third law, that is Boyle's law. Boyle's law. Now third variable, that is temperature, that should kept constant. For fixed mass of a gas at constant temperature, the volume of given mass of a gas is inversely proportional to its pressure. Means volume increases, pressure decreases. Volume decreases, pressure increases due to inverse proportion. And when inverse proportion is there, product of these two variables that is always remains constant. Always keep in mind that. Understood? Then suppose this is equation number 1 and this is equation number 2. Then combining equation, in this case volume is inversely proportional to pressure. Consider equation number 1, then consider equation number 2. In this case volume is directly proportional to temperature, and according to Boyle's law volume is inversely proportional to pressure. Now combining these two equations, we can write volume is directly proportional to temperature and it is inversely proportional to the pressure. And now to remove this proportionality sign, we have to put constant, and that constant is R, that is universal gas constant. And rearranging this equation, we can write PV that is equal to RT, and this is for 1 mole of a gas. Now for n mole of gas, we can write PV that is equal to nRT, and R is the universal gas constant and its value is 8.31 joule per kilo mole. And this is the value of universal gas constant, and this is the ideal gas equation for 1 mole of a gas, and this is ideal gas equation for n mole of a gas. And in this manner we can obtain the ideal gas equation by using these 3 laws: Charles law, Gay-Lussac's law and Boyle's law. I hope all of you understood this ideal gas equation very well. Now we have to study about the thermal equilibrium. Thermal equilibrium. Before studying that point, we have to define 2 definitions. First is absolute zero scale. Absolute zero scale and triple point of water. Absolute zero scale, absolute zero scale and triple point of water. Absolute zero scale and triple point of water. absolute zero scale, it is a scale or it is a temperature below which it is not possible to cool any substance. Means that is the lowest temperature. We know that if the temperature becomes 0 and after that temperature becomes -1, -2 up till it becomes -273.15, and this temperature, that is called as a absolute zero scale because the temperature below which it is not possible to cool any substance, means the lowest temperature, that is called as absolute zero scale. असं टेम्परेचर की ज्याच्या खाली पदार्थ थंड करणं शक्य नसतं त्या टेम्परेचरला कोणतं स्केल म्हणायचं? ॲब्सोल्यूट झिरो स्केल. ओके. अँड ट्रिपल पॉईंट ऑफ वॉटर. ट्रिपल पॉईंट ऑफ वॉटर, that is a point. Suppose this is a graph and this is a triple point, and triple point of water, it is a point at which the water in solid, liquid and gas form, solid form that is ice, solid form of water that is ice, liquid form that is water, and gas form that is vapor, gas form that is vapor. And triple point of water is a point at which water in a solid, liquid and gaseous form that can coexist in equilibrium. असा पॉइंट की ज्या ठिकाणी आपल्याला पाणी हे तिन्ही स्वरूपात अस्तित्वात असलेलं सापडतं, कोएक्झिस्ट होतं, त्या पॉइंटला काय म्हणायचं? ट्रिपल पॉइंट ऑफ वॉटर. अँड दिस इज द डेफिनेशन ऑफ ट्रिपल पॉइंट ऑफ वॉटर. ओके. नाव वी हॅव टू स्टडी द थर्मल इक्विलिब्रियम. थर्मल इक्विलिब्रियम. थर्मल इक्विलिब्रियम. Thermal equilibrium. Suppose this is a solid and we increase the temperature of this solid. At that time what happen? The intermolecular distance between this solid that gets increased, and when this intermolecular distance that gets increased, its dimension change. Understood? When intermolecular distance between the solid molecules that increased, then its dimension is changed. Means when a temperature is increased, dimension of that solid that gets changed, and increase in dimension due to increase in temperature is called as thermal expansion. Sorry, thermal equilibrium, thermal expansion. Sorry. Thermal expansion. Understood? What is the definition of thermal expansion? The increase in dimension due to increase in temperature, that is called as a thermal expansion. Now, when we supply heat to, or when we increase the temperature, at that time sometimes the length gets increased. When length increased, at that time that is called as a linear expansion. When length gets increased, it is called linear expansion. When we increase the temperature of solid, its area gets increased. That is called areal expansion or superficial expansion. Superficial expansion. And when we increase the temperature, its volume gets increased. Therefore, it is called volume expansion, or it is also called as cubical expansion. Understood? When we increase temperature, length gets increased, that is called linear expansion. When area increase, that is called areal expansion or superficial expansion. And when its volume gets increased, that at that time that expansion is called as volume expansion or cubical expansion. Now we have to study in detailed manner one by one each expansion. Now first, linear expansion. And if you understood one type of expansion, automatically you will understood the superficial expansion or areal expansion and volume expansion. Then first, linear expansion. Linear expansion. Linear expansion. Suppose consider a rod that is having length L, and if we increase its temperature to delta L, this is L is the original length of that rod, and if we increase the temperature delta T, L is original length, delta T, that is increase in temperature, and its length becomes L plus delta L. Means what is the increase in length? L plus delta L minus L, that is equal to delta L, that is increase in length, delta L, that is increase in length. This L is original length, delta T, that is rise in temperature, and delta L, that is change in length, Now, delta L by L, that is called fractional change in length. Understood? Delta L by L, that is called fractional change in length, and it is directly proportional to rise in temperature. This fractional change in length, that is directly proportional to the rise in temperature. And to remove this proportionality sign, we have to put constant, and that constant is called as alpha, that is coefficient of linear expansion. This alpha is called coefficient of linear expansion. Now, consider a second case. In that case, L0, that is the original length at T0 temperature. This is the initial temperature. And when we increase the temperature, that is T is the increase in temperature, and at that time length is LT. Now LT minus L0, that is increase in length, and T minus T0, that is rise in temperature. Therefore, this delta L by L, that is nothing but LT minus L0, and this original length, that is L0, that is equal to alpha into delta T, that is nothing but T minus T0. Now rearranging this equation, we can write alpha, that is equal to LT minus L0 divided by L0 into T minus T0. This is the formula for the alpha. Now, unit of LT minus L0, that is meter, and unit of L0 is also meter. This meter and this meter, that gets cancelled, and the SI unit of alpha, that is equal to 1 upon degree Celsius or 1 upon Kelvin, and that is nothing but the SI unit of alpha, degree Celsius inverse or Kelvin inverse. That is the SI unit. And what are the dimension of alpha? Dimension of alpha, that is 1 upon temperature, that is nothing but L raised to 0, M raised to 0, T raised to 0, and K raised to minus 1. Means exactly opposite to dimension of temperature. Dimension of temperature is K raised to 1, and dimension of the alpha, that is K raised to minus 1. And if you have to write the experimental formula for the alpha, we can write, suppose at temperature T1, L1 is the length, and when we increase the temperature up to T2, at that time length is L2. And now experimental formula for the alpha can be written as alpha, that is equal to L2, in this manner, increase in length, that is L2 minus L1, original length, that is L1, and rise in temperature, that is T2 minus T1. This is the experimental formula for the alpha. Now we have to define the coefficient of the linear expansion. This alpha, that is called coefficient of linear expansion. When T minus T0, that is 1 degree Celsius, at that time we can define, means LT minus L0, that is called increase in length. L0, that is called original length at 0 degree Celsius. And if T minus T0 is 1 degree Celsius, at that time we can define coefficient of linear expansion. What is the name of alpha? Coefficient of linear expansion is defined as increase in length per unit. Divide ला काय म्हणायचं? Per unit. Increase in length per unit. Original length at 0 degree Celsius for 1 degree rise in temperature. And that is the definition of coefficient of linear expansion. Understood? I repeat. Coefficient of linear expansion is defined as increase in length per unit original length at 0 degree Celsius for 1 degree rise in temperature. And in this manner, I try to explain a thermal expansion, and in that thermal expansion, first type, that is the linear expansion. And if you understood this concept very well, then you can easily understand the concept of the areal expansion and volume expansion. Okay, now let us study the second type, that is areal expansion or superficial expansion. Areal expansion or superficial expansion. Now for that purpose, consider a square plate. This is the square plate, and its original area is A. Original area is A, and delta T, that is rise in temperature, and A plus delta A, that is increase in its area. Now always keep in mind that linear expansion, that is one dimensional expansion, and areal expansion, that is two-dimensional expansion. And now A is the original area. Instead of length only you have to replace area here. Then delta T, for delta T rise in temperature, the delta A, that is change in area. Change in area. Change in area. Then delta A by A, that is fractional change in area, that is directly proportional to rise in temperature. Delta T, that is rise in temperature. Now delta A by A, that is equal to, now to remove this proportionality sign, we have to keep constant, and that constant is called as beta. And this beta is called coefficient of the areal expansion and coefficient of areal expansion. Now again consider the area A. Area A0. This is the area A0 at initial temperature T0, and when we increase the temperature up to T, then area is AT. AT is the area. Then instead of L only we have to change A. AT minus A0 increase in area, T minus T0 rise in temperature, then AT minus A0 divided by A0 into beta into T minus T0, and then beta, that is equal to AT minus A0 into divided by A0 into T minus T0, and this beta, that is called coefficient of areal expansion or coefficient of superficial expansion. Again the AT minus A0, that is having unit meter square, then unit of this A0, that is meter square, and unit of temperature, that is degree Celsius. Then this meter square, that gets cancelled, and again unit of beta, SI unit of beta, that is 1 by degree Celsius, and if temperature is expressed in degree Kelvin, at that time it is 1 by K. Means again the SI unit of beta, that is degree Celsius inverse or Kelvin inverse. Then again dimension of beta, that is equal to this one, L raised to 0, M raised to 0, T raised to 0 and Kelvin raised to -1. Then the experimental formula, again consider the case A1, that is the area, A1 that is the area at T1 temperature, A2 that is the area at T2 temperature, and experimental formula we can write for beta, that is equal to A2 minus A1 divided by A1 into bracket T2 minus T1. This is the experimental formula for the coefficient of areal expansion or coefficient of superficial expansion. Now we have to define the coefficient of superficial expansion, that is beta. Now for 1 degree rise in temperature, if we substitute T minus T0, that is equal to 1, at that time only we have to replace, instead of length we have to replace a word area, and therefore we can define the coefficient of areal expansion, that is increase in area per unit original area at 0 degree Celsius for 1 degree Celsius rise in temperature. And this is the definition of the coefficient of areal expansion. Now we have to study the third expansion, that is the cubical expansion. Cubical expansion. Cubical expansion. Cubical expansion. Now consider a cube. This is a cube. This is a cube. Then V is original volume, and if we increase the temperature up to delta T, then increase in volume, that is V plus delta V. For delta T rise in temperature, volume becomes V plus delta V, and therefore delta V is increase in volume. Then V is the original volume. Instead of area, only you have to change a word, that is volume. Original volume. Delta T, that is rise in temperature. Delta V, change in volume. Change in volume. 1 minute. Change in volume. Then delta V by V, that is directly proportional to rise in temperature. Delta V by V, that is equal to, now to remove this proportionality sign we have to put constant, and that constant is called as gamma, and this gamma is called coefficient of cubical expansion. Now the coefficient of cubical expansion. Now consider the volume at 0 degree Celsius, volume is at 0 degree, means T0 temperature, volume is V0, and at the T degree Celsius, volume is Vt. Volume is Vt, and therefore we can write Vt minus V0, Vt minus V0, that is increase in volume, T minus T0, rise in temperature, Vt minus V0 upon V0, that is equal to gamma into T minus T0. Rearranging this equation, we can write gamma, that is equal to Vt minus V0, Vt minus V0 divided by V0 into bracket T minus T0. And from this, the SI unit of gamma, that is also the unit of this volume, that is meter cube, SI unit meter cube. Original volume is also in meter cube, and unit of temperature, that is degree Celsius. Then this meter cube, that gets cancelled, and SI unit of gamma, that is nothing but the 1 upon degree Celsius, or when this temperature is expressed in Kelvin, it becomes 1 upon Kelvin, that is nothing but the SI unit of gamma, that is degree Celsius inverse or Kelvin inverse, and from this the dimension of gamma, that is equal to L raised to 0, M raised to 0, T raised to 0, Kelvin raised to -1. And for the experimental formula, suppose V1 is the volume at temperature T1, then V2 is the volume at temperature T2, then experimental formula for gamma can be written as V2 minus V1 divided by V1 into bracket T2 minus T1. Now we can define the coefficient of cubical expansion or coefficient of volume expansion. What is the definition of the coefficient of cubical expansion or coefficient of volume expansion? When T minus T0, that is 1 degree Celsius, at that time the coefficient of cubical expansion or coefficient of volume expansion is defined as increase in volume per unit original volume at 0 degree Celsius for 1 degree rise in temperature. And this is the definition for the gamma or coefficient of cubical expansion. Linear expansion, that is one dimensional expansion. Areal expansion, that is two dimensional expansion, and volume expansion, that is three dimensional expansion. And when we supply heat to any solid and it expands equally in all direction, that is called isotropic solid, and all metals are the isotropic solids. Understood? I hope all of you understood these three types of thermal expansion very well. Now we have to obtain the relation between alpha and beta, and later on relation between alpha and gamma. First, relation between alpha and beta. Relation between alpha and beta. Relation between alpha and beta. Now we already studied that LT minus L0 divided by L0, that is equal to alpha into delta T. Alpha into delta T. Now rearranging this equation, we can write the LT minus L0, that is equal to L0 alpha into delta T. And if we transfer this L0 here, we can write L0 plus L0 alpha into delta T, that is nothing but LT, that is equal to, if L0 is taken as common, 1 plus alpha into delta T. This is equation number 1. Now to obtain the relation between alpha and beta, means relation between coefficient of linear expansion and coefficient of areal expansion, consider a area, and at a 0 degree Celsius the length of this square, that is L0, and its area is A0, and this A0, that is nothing but L0 square at 0 degree Celsius. When we increase the temperature, that is up to delta T, suppose that at T degree Celsius the area is AT and length becomes LT, and therefore this area, that is nothing but LT square, length square. Now we know that the LT, that is equal to L0 1 plus alpha into delta T. Now squaring equation number 1, we can write LT square, that is equal to L0 square 1 plus L0 square 1 plus alpha into delta T square. According to binomial expansion, LT square, that is equal to L0 square 1 plus twice alpha into delta T plus alpha square delta T square, but alpha is very small and therefore its higher term that can neglected and therefore we can neglect this term. Then we know that L0 square that is equal to A0, LT square that is equal to AT, and inside bracket 1 plus twice alpha into delta T. This is equation number 2. Now in case of a aerial expansion, we already studied that AT that is equal to A0 1 plus beta into delta T. Comparing equation 2 and 3, we can write beta that is equal to twice alpha, and this is the relation between coefficient of aerial expansion and coefficient of linear expansion. Understood? Now we have to obtain the relation between alpha and gamma. For that purpose, consider a cubical container. A cubical container. This is a cubical container. This is a cube. Then we know that cube is made up of with the help of 6 faces. They are square in shape and length of each side of the square, that is L0, at 0 degree Celsius. At 0 degree Celsius, its length is L0 and therefore volume V0 that is equal to L0 cube. When we increase its temperature up to delta T, then the length becomes, at a T degree Celsius, its length becomes, that is LT, and volume VT that is nothing but LT cube, length into breadth into height. Now volume of this cube at T degree Celsius that is equal to LT cube. Now we already studied that relation between LT and L0, that is nothing but LT that is equal to L0 1 plus alpha dt. Now make a cube of this equation, cube. Then according to binomial expansion, cube of this equation that is equal to 1 plus thrice alpha into delta t plus alpha cube delta t cube plus thrice higher power of this alpha term that can be neglected, and therefore we can neglect all this term and only 3 alpha into delta t that remains here, and that is nothing but the LT cube. We know that LT cube that is nothing but the VT, then the L0 cube that is equal to V0, and here 3 alpha into delta t. This is equation number 2. Now we already studied that Vt into V0 that is equal to 1 plus gamma into delta t in case of a volume expansion or cubical expansion, and therefore the comparing equation 2 and 3, we can write the gamma that is equal to 3 alpha, and this is the relation between the gamma means coefficient of cubical expansion and coefficient of linear expansion, and combining these two equations we can write the alpha that is equal to beta by 2 and gamma by 3. This is the relation between alpha, beta and gamma, and we can write this equation in this manner: alpha as to beta as to gamma that is equal to 1 as to 2 and 2 as to 3, and this is the relation between the alpha, beta and gamma, 1 as to 2, 2 as to 3, and in this manner we can explain the thermal expansion and relation between alpha and beta and alpha and gamma. I hope all of you understood all these concepts very well. If you like this video, then like, share with your friends, and Also subscribe my channel so that you will get notified about my new upcoming videos, and put down the comments in the comment section below. Thank you for watching this whole video. Okay, thank you once again.